Hi, my name's Ashik Duria, and this is my Physics 2212 Lab 5 report on Faraday's law and falling magnets. To begin this presentation, I'll go through this overview, including an introduction, purpose and main results, important related concepts, the actual experiment, including a computational model made with GlowScript, the results from that model, and then I'll end the presentation off with a short discussion. The purpose of this lab is to collect observational data of a magnet falling through a conductive tube of aluminum foil, then to model this magnet and tube interaction computationally, and then compare the computational predictions with the observed data. The results of the experimental time and computational time of the magnet falling through the aluminum tube are given below. Some important concepts necessary to know for this lab is the ideas and formulas corresponding to the magnetic field of a bar magnet, as well as magnetic flux. Additionally, Faraday's law, Ohm's law, Lenz's law, and the magnetic force on a falling magnet caused by a current-carrying loop. The associated and necessary formulas are also shown here. The image on the right closely resembles the experiment going on in this lab. I basically dropped a bar magnet through a tube of aluminum foil. This data listed on the left of the illustration gives dimensions to the experiment, which is needed to create the computational model discussed in the following slides. The values of the magnetic moment of the bar magnet was found in Lab 3, and the average time through the tube was found through about 5 or 6 experimental trials. This experiment brings up the following questions. Why can't we use a ferrous tube, for example, a steel pipe? Well, a ferrous tube contains iron, which becomes induced, causing interference with the falling magnet. What happens to the magnet, and how does this compare to a magnet falling in free space without a tube? Well, with a ferrous tube, the magnet falls slowly through the tube, slower than if dropped in free space in the absence of that tube. In the code for the computational model, I first input the initial values of the geometry of the tube that I specified in the previous experiment slide. I then created a function to calculate the magnetic field of the bar magnet. I then wrote a function to calculate the magnetic flux and calculate the current in a single ring. Steps 5 and 6 include creating a function to compute the typical magnetic field at each ring. Then I calculated the gravitational force and net force on the magnet. And lastly, I had to update the magnet's velocity and position. These are the results from the computational model. From this model, it's determined that the computational time in the tube is 1.034 seconds compared to my calculated average time of 1.25 seconds. In this lab, we have quite a few questions to go over, so I'll answer them one by one, respectively to how they are organized on the slide. According to Lenz's law, the way to slow down the magnet relates to red, corresponding to counterclockwise, and blue, clockwise. If we were to flip the magnet around, the current would flow in the opposite direction, though the magnet would still react in the same way. In this lab, my experimental data and computational data were fairly similar, though accounting for air resistance might yield a more accurate reading, as well as counting multiple rings around the aluminum tube. The shape of the velocity time graph shows us that in the beginning and the end of the experiment, the forces are unbalanced, though through the intermediate time of the experiment, the forces seem to balance out. If the resistivity of the conductor was reduced close to a value near 0, the braking force would increase to a point where it balances the gravitational force and prevents the magnet from falling through the tube. If holes were made in the tube, I presume that the current flowing through the tube would be reduced because there would be a loss of current in some loops, therefore resulting in a weakened braking force. Thank you so much.